And just like section 6.1, section 6.2 contains a bonus triangle area formula. So this is a formula named after Heron or Hero of Alexandria, who lived in the 1st century AD. And he figured out this way of calculating the area of a triangle if you know only the lengths of the 3 sides. The common formula for the area of a triangle, you have to know the base and the height. And then the area is 1/2 times base times height. But what if you don't know the height, but you do know the 3 sides of the triangle? Then you can use this rule to calculate the area. So it's kind of a 2-step formula. Step 1, you calculate the semi-perimeter, A plus B plus C divided by 2. The perimeter would be all the way around the triangle, so it would be just the 3 sides added together. If you divide that by 2, you get the semi-perimeter, which is halfway around the triangle. So that's what S stands for. So then to calculate the area, you take S times S minus A times S minus B times S minus C, and then after multiplying that all together, you take the square root and you get the area. Now, I'm not going to explain why this formula works, but I may give you a link to a proof or an explanation elsewhere online that you can look at if you want to. You don't have to. But let's try this formula out on, well, that triangle we were just working with. If we know the sides are 11, 13, and 15, now we could figure out the angles. In fact, we did in the previous video, but forget that. If we wanted to, we could figure out the angles and then use that formula from last time to get the area. But if we just know the sides and we don't want to mess around with angles, we can use Heron's formula. So step 1, the semi-perimeter here would be 11 plus 13 plus 15 divided by 2. So that comes out to be 39 divided by 2, or 19.5. So all the way around the triangle, 39 units. Halfway around, 19.5. Now the area is the square root of 19.5 times 19.5 minus 11 times 19.5 minus 13 times 19.5 minus 15. And when you put that all into your calculator and work out what you get, it comes out to be 69.6. So that is the area of that triangle, 69.6 square units. Now a couple of applications. Stolen from the book, this is number 38. Determine the angle theta in the design of the street light shown in the figure. So we've got this angle between the pole that the street light is on and this rod up here to the light. We want to know what that angle is. If this has a length of 3, this is 2, and this is 4.5. Notice how that is a triangle. So we have a triangle where we know 3 sides of the triangle, and we want to find an angle. And we've done things like that before. That was one of our Law of Cosines examples. So putting the 3 sides that we know into the formula for the Law of Cosines, making sure that the special side, the side that is on one side by itself, or the side that's subtracted rather than added, is the side that is opposite the angle that we're looking for. Like if this is angle A, then side A would be the one that's 4.5. So then the cosine of theta is 3 squared plus 2 squared minus 4.5 squared divided by 2 times 3 times 2. That comes out to be negative 0.604, which is okay. And when you take the arc cosine of that negative number, you get 127.2. You get an obtuse angle, which is what it looks like in the picture. So that's an angle of 127.2 degrees. Let's try another example. A 100-foot vertical tower is to be erected on the side of a hill that makes a 6-degree angle with the horizontal. Find the length of each of the two guy wires that will be anchored, oops, typo, that should say 75 feet uphill and downhill from the base of the tower. So here's our picture, and I've made it real clear where our triangles are. So we've got what we're trying to find is the length of this guy wire over here. That's what I've got labeled A1. And this one over here is A2. And then I drew in some triangles. So there's 2 triangles, 3 in all, but we'll work with the 2 smaller ones. So the one on the left, this side is 100 feet. And this side is 75 feet. And if the tower were straight up and down, then this would be a 90-degree angle. And in that case, we could use the Pythagorean theorem to find the hypotenuse of that right triangle. We'd have 75 squared plus 100 squared equals whatever this is squared, and we can work out what this is. In fact, it would turn out to be 125 feet. But it's not quite a right angle. It's 6 degrees more than that on this side, and then on the other side, in the other triangle, it's 6 degrees less than that. So for the triangle on the left, this angle that is between the 2 sides that we know, so it's like if this is angle B, then the sides are, or if this is angle A, then the sides are B and C. And the angle between those 2 sides is a 96-degree angle. It's 90 degrees plus 6 more for the downhillness. So by the law of cosines, A1 squared equals 100 squared plus 75 squared minus 2 times 100 times 75 times the cosine of the angle between the 100 and 75-foot sides. So from that, by calculating that out and taking square roots to get A1 itself, we get that this guy wire is 131.1 feet. Remember I said if this were on level ground, we'd have a right triangle. We could use the Pythagorean theorem and get that this was 125 feet. Because it's sloping, it's a little bit longer than that, so it turns out to be 131.1 feet. And then the other triangle on the right, to find A2, law of cosines again, A2 squared equals 100 squared plus 75 squared minus 2 times 100 times 75 times the cosine of 84 degrees. Because now the angle here is a 90-degree angle minus the 6 degrees that the hillside is angled up. So from that, we do the calculations, take the square root to go from A2 squared to just A2, and we get that this guy wire is 118.6 feet. So that's section 6.2.